Hi everyone, this is Professor Lovell, and today we are going to go from talking about dispersion to really understanding what standard deviations are, and then a more theoretical but important concept of the normal curve and how that is useful in basic statistics. The normal curve is going to be a requirement to a lot of the inferential statistics that we do, and so it's important that we really grasp the concept of the connection between standard deviations and the normal curve. So to get to the standard deviations, again, this was covered last lecture, but I want to go through why are we talking about a standard deviation? Why is it an important and the most useful measure of dispersion versus other measures? And then we'll talk about how that goes into the normal curve. So, as a reminder, a frequency distribution is the number of cases for every value for a variable. And when you graph them, it gives you the frequency curve. So when we're describing a frequency distribution, we're trying to both describe where the center of that distribution is, and that is where we covered mean, median, and mode. And we're trying to describe the dispersion, so how wide, how far away from that center, and is it equal on each side, or is there kind of a skew? So the first dispersion measurement that we could use is the range, which takes the highest score minus the lowest score. So it just gives us how long is this distribution. Now the problem with that range is that it only tells us where the minimum and the maximum are. It does not tell us anything about what's going on in the middle or how far away. So each of these graphs could be the same range, even though they look very different. So next, we could shorten that range, and that's what the interquartile range does, is it gives us a measurement of the middle 50% of the distribution. You break up the distribution into quarters or quartiles, so you find the smallest 25%, then the next 25%, so on and so forth. And you take the range between the 75th percentile and the 25th percentile. Now again, the problem with that is it still only measures, you get a number that only tells you between the 75th and the 25th percentile. So it's really just a shorter range, right? It ignores what's going on the farthest ends and really just tells you what's going on in the middle. The problem is, depending on the way your graph looks, you might have something that actually is still similar. So A and B probably have similar interquartile ranges here because the very small parts on the end will be ignored while everything else is within the 25th and 75th percentiles. So to fix the issues of just counting 2 points, subtracting them and finding how far away they are from each other, that's both the range and the IQR, we're going to talk about deviation. The deviation is the distance between a value or a case and the mean. So the mean is the statistical average, right? You take all of the you take all of the observations, add them up, and then divide them by the number of counts. And when you then, to get the deviation, is you pick one of those cases. So in this case, we like a hypothetical case we call x of I, and you take x of I minus x bar, which is the mean, and that is the deviation. So the distance between that case and the mean. The problem is this only gives us one value, and we're trying to create a statistical measure that describes the entire dispersion of a frequency distribution. We want to know exactly, we want to have an easy statistic that provides all of the information about the dispersion with one number. So this would only give us one value, it would give us one number, but it's only about one case instead of every single case that's part of the frequency distribution. So one option is adding up every single deviation. So we would take the mean and then we would find multiple cases, like every single case, and we would find how far away it is from the mean, and then we would add them all up. The problem is that, as we talked about, one of the characteristics of the mean is that it is the exact center of gravity. That means there is exactly the same amount of weight on the right side of the mean as there is on the left side of the mean. So when you take deviations that are greater than the mean, those deviations are going to be positive numbers. And when you take deviations that are smaller than the mean, they're going to be negative numbers, right? So in this case, we have one example of x2 is 55. And when you take 55 minus the mean, 55 minus 60, you get a negative 5. And so since all of the values above the mean are positive and all the values below the mean are negative, and they are the exact same weight, they cancel each other out. So the sum of deviations will always be 0. There is no exception to this. They will always be 0. So we need to find a way to measure the dispersion that doesn't just equal 0. So how do we add the deviances without them equaling 0? The best way, and so there are a couple of ways, but the best way for statistics is squaring every value. And if you're familiar with just algebra, and even before algebra, statistics or math, when you square a negative number, it always makes it positive, because when you multiply two negative numbers, you get a positive. So if you had negative 5 squared, that would be negative 5 times negative 5, which equals positive 25. So in this case, we do the same thing. It's just that we square the deviation. So we have 5 squared and then negative 5 squared, which both equal 25. You add those up, and you add up every single case's squared deviation, and then you would get your final sum of squared deviations. There is a little bit of a problem with that, because since it's an additive function and since every value is going to be positive, if you have a really large data set, so if you have more cases, more values, then it will end up looking like it has a bigger variance, like a bigger, or not a bigger variance, a bigger dispersion. It will look like it's farther, like there are more cases farther away from the mean than if you had a smaller data set. And so here is a quick example. On the left is a small data set that is only 36 cases, where on the right is a large data set that has 360 cases. If you look at the table, the deviance is the same, the mean is the same, the deviance squared is the same, but when you add all of the deviance squared up, for the large data set, it is since it's 10 times the number of cases, it is 10 times the variance, or the dispersion. So the sum of squared deviances for the large data set seems to be 295, whereas the sum of squared deviance for the small data set is only 29.5. So it's a big difference, and that really makes it hard to compare large and small data sets if you're only using the sum of squared deviations. So we need to find a way to be able to compare a large data set with a small data set. And the way you do that is by dividing it by n. This is called standardizing. So since you're adding every value's distance from the mean, if we subtract by the number of we divide by the number of values, then we actually are able to we're able to control for that. It's the same way we get the mean, right? When you add up all of the values and divide it by the number of values, that way you can compare between two different averages. This is something similar. So you add up, like we did before, all the squared distances between the value and the mean, and then you divide it by the number of cases. So this is an example of what I just showed you with the small data set and the large data set. On the small data set, we take the sum of squared deviances, 29.5, and we divide it by 36. That was the number of cases. And we come out with a variance. So this is the standardized sum of squared deviations of 0.8197. Now, when in the next data set, the large data set, remember the sum of squared deviations was 295, and we divide it by the larger n here, 360, and we actually come out with the same variance, so 0.8197. So the variance actually solves the problem of the large versus small cases in data sets. There is one small problem, though, that we still have to reconcile. Deviation and sum of deviations keep the same units that you would have. But because the sum of squared deviations and this variance squared, or in the variance square the dispersion measurement, it creates a weird unit. So let's say that this graph on the right is a distribution of age. So we have 55, like 60 is the mean age in this data set. When you're doing all of these calculations of deviance, of sum of deviations, of the sum of squared deviation, you're still working in terms of years. So when you take x1 minus x bar, you are taking 65 years minus 60 years, and your deviance is 5 years. When you're doing the sum, it's, again, you're taking the -5 plus 5 years, and that equals 0 years. So the problem is when you then square it, doing the sum of squared deviations, now you're working in units of years squared rather than just years. And that creates a question of like, what does it mean that the variance is 25 years squared? That's hard to reconcile. It's hard to say this data set varies by 25 years squared. That's a weird, way to think about it. And so the simple answer here is to take the square root. So this is called the standard deviation. So you take the variance, which again is the sum of squared deviations, and divide it by n, and then you take the square root of that variance. And what that does is it takes the years squared and puts it back into years, and now we have a value, a single number that explains the entire dispersion of a distribution. So in this distribution, the variance, the dispersion of this distribution is 5 years. That means the average case is 5 years away from the mean. Okay, that tells us that the average case is 5 years away from the mean. So that is how we get to the standard deviation and why we get to the standard deviation. It clears up a whole bunch of different issues. Here is an example of what is going on with the standard deviation. I will let you pause this and kind of read through this. But when we get to in this case, we're studying GPA here, and the standard deviation comes out to 0.905, and so the average deviation from the mean is about 0.905 grade points. That means, so the average case is about 0.905 points away from the mean. Okay, so again, this is the chart that you had in the last one. It shows you all of the measures of dispersion that we've discussed from the range to the standard deviation, and it gives you its use as well as the problems with it. So feel free to review this, and the PowerPoints are online so you can copy and save this table. So let's talk about the normal curve and why the standard deviation here is important. So the normal curve is theoretical, but it describes a curve in which there is a single peak. So that means there's one mode. It is symmetrical. That means the mean, median, and mode are all the same number. So the most frequent number, the perfect middle in terms of if you line up all of the values from smallest to greatest, it's the one straight in the middle. And the mean is the center of gravity, the one that has the equal amount of values from the left to the right. It is bell-shaped, and What makes a distribution curve normal is that a standard deviation above the mean is equal to a standard deviation below the mean. It's the same distance between that. It's required to be symmetrical, right? If it was skewed in any way, a standard deviation above the mean would not be the same as a standard deviation below the mean. So the normal curve is distributed among specific areas of standard deviation. So on a normal curve, the first standard deviation is about 34% of the variable's cases. So we see this on this chart. You have the mean is at the 0 standard deviations. It's 0 because the mean is, the standard deviation is measuring the values dispersion away from the mean. So if you had cases at the mean, they would have a standard deviation of 0. And 34% of the cases lie within one standard deviation above, and another 34% of the cases lie within one standard deviation below, right? So this is just a property of the normal curve. Remember, this is theoretical. So they are saying if we have this perfect bell curve, these are the attributes of that perfect normal bell curve. 34% of the cases are one standard deviation above, and 34% of the cases are within one standard deviation below. Then, when you go to the from one standard deviation above to two standard deviations above, there's about 13.5% of the cases, and so on. So this will always happen when you have a perfectly normal curve. Now, rarely does a perfectly normal curve exist in the world, but this is, like I said, this is a theoretical example. So, some people call this the 68, 95, 99 rule. I think that is just as difficult to remember and understand. So just keep in mind that you can always come back to this to remind yourself what that means. It's saying that 68% of a data set or of a variable's cases will land between the one standard deviation above and one standard deviation below the mean. 95% of the cases in a variable will land between two standard deviations above and two standard deviations below the mean. And then 99.7% of the cases will land between three standard deviations above and three standard deviations below. So remember, as we're talking about the area under the normal curve, this is the percentage of cases in a variable. So we have to remember that what a frequency distribution is doing is adding up all of the cases for every possible value, and then we're putting a line to it, right? And so that's why it is all the percentage of cases in a variable. So many variable distributions that we will see are fairly close to normal curves. They're close enough that we will be able to treat them as if they were normal curves. And they're going to be very powerful in inferential statistics when we do some sampling. So sampling requires a normal curve, and we'll see how the theories behind sampling actually produce a normal curve. Okay, so one of the weird things is talking about a z-score. So standard deviations are useful for comparing variables in data sets. As we said, it reduces the units back to their normal unit level. It avoids the issue of large and small data sets. But the values we want to compare are rarely full integers like this is one standard deviation away from the mean. Usually they're at like a really awkward number like 1.639, right? And so where we can know that between 0 and 1 standard deviation of the mean is about 35% of the cases, it's hard to know what 1.639 standard deviations, how many cases are between that and the mean. And so statisticians have created something for that. It's called the z-score, in which when you find your standard deviation, the z-score the same thing, but you can use it to convert the percentage of, you can use it to calculate the percentage of cases within the area under the curve, okay? So this is how a z-score works. It takes our original unit, like GPA or age, and standardizes it to a normal distribution that has a mean of 0 and a standard deviation of 1. The theory behind this isn't too important, but just remember to get the z-score is instead of, it's kind of like the deviation equation, is that you take the case number minus the mean, and instead of dividing it by n, or you divide it by s, which is the standard deviation. Okay? To do the z-score in R, you can just take that calculation. So you take an observation minus the mean and divide the standard deviation. Here I created objects of the observation, mean, and standard deviation, and then I created the equation here. You can just do 3.2 minus 2.89 and then divide it by 0.905. In any case, if we have an observation of 3.2 with a mean of 2.89 and a standard deviation of 0.905, this z-score will be 0.34. So z-scores help us find the area under the normal curve. So when would we need to know this? Here is an example of a data set. This was the large sample of GPAs at a high school that we've been using. And I have the frequency distribution graphed on the right. So let's just pretend this is a normal curve. Let's assume that Sarah is at the school and she got a 3.2 GPA. She wants to know how she ranks in comparison to the rest of the school. And so we're going to find her z-score. We take a 3.2 GPA, we subtract it by the mean, which you can see on the bottom left of the table. The mean is 2.89, and then we divide it by the standard deviation. And so her z-score is 0.3425. Now, using the z-score in a function in R, we can then find what percent of cases are above and below the z-score. The function in R is called pnorm, and this is a command where you can input the data used for a z-score and find the area under the curve. The way it works is for pnorm, you do pnorm parentheses, you put in the observation, so in this case it's Sarah's GPA at 3.2, you put in the distribution's mean, which is 2.89, and then you put in the distribution standard deviation, which is 0.905. Then that gives you the proportion of the area under the curve smaller than that observation. So 0.63 means that Sarah is doing better than 63.31% of the school. So we know where that exact value falls within the distribution and how many is above and below. So let's do another example. Federico has had a rough semester and he ended with a GPA of about 2.6, and he also wants to know how he ranks. So here you can calculate the z-score again, and using pnorm, I have on top, this is an example of just putting in the equation for the z-score. And then we can see that the p-norm uses the same information for calculating the z-score. It just does a different little thing behind the scenes that you don't need to know. But the p-norm gives us 0.374, meaning that for Federico, his GPA of 2.9 is about 37.4% higher, or is it higher than 37.4% of the class? It also means that he's doing worse than about 62% of the class. So this could be helpful if you, for example, are a manager looking at your sales staff, and you want to know if a certain sales staff is doing better than 80% of the rest of this department. Perhaps you want to know how well a certain product is doing compared to a bunch of other products in your company. So this is a very useful tool both in statistics and in the real world. We can also find how many people in their class, in Sarah and Frederico's class, have a GPA between them. And this you just do by subtracting the higher GPA or the lower GPA from the higher GPA, or the higher z-score p-norm from the lower z-score p-norm. So remember, these are the 0.634 are the results from the p-norm and the 0.374. So we subtract those from each other, and we find out about 26% of students are falling between Federico and Sarah. To see this on the graph, we see that Sarah's score of 3.2 has about, I'm trying to think of 63%. There it is. So it's all of this yellow here on the left, whereas Frederico is higher than about 37%, this area in green, and we want to subtract the area in green from the area in yellow, and that will leave us this small sliver in between the two z-scores. So if we take 0.634 minus 3.37, we see that 26% of GPAs fall between Frederico and Sarah's. So that is it for today. As this was fairly fast, I just noticed. I didn't realize that it's going to go that quickly. So feel free to go back, take your time to read through the slides, make sure you understand. And if you have questions, bring them to class on Thursday. Thanks, everyone. We'll see you then.